Please write your enrollment number in the chat box.
Good morning, sir.
Good morning. Those who have already written and again write. Please again write your enrollment number in the chat box.
topic minus topic. Okay. Good morning to everybody.
Good morning, sir.
So,
Morning, sir. Good morning, sir.
okay.
Good morning, sir.
Thank you. Good morning. Okay. The last class we have already discussed about an important property of electromagnetic wave, that is your interference, and we have taken the electromagnetic wave as light. Okay. Today we'll go for another important property of a wave. While I am giving the introduction, I have told you the three important property of the electromagnetic wave will be discussed, and that one property is your polarization, already discussed in the first class, and next property interference in the last class, and today we'll go for the another important property, that is your diffraction. So what is the diffraction? What is that diffraction? Let's come to diffraction. Just it is the a property of light by virtue of which light propagates in straight line. Light moves along a straight path, but you see light also bent under certain condition. Light propagates in a straight path, but light moves in a straight line. In your school class, light moves along a straight path. Light moves along straight line. But in this chapter, you'll see that light also bends at certain condition. What is that condition? When you take a obstacle, is an obstacle on the path of the light. Obstacle, that is the substance through which light cannot propagate through. The substance through which light cannot propagate through, that is called obstacle or opaque object. So when you place a obstacle on the path of the rays, this is a source of light, here is a obstacle is here, so that a shadow will form on the screen. You notice shadow of
Hello,
that
sir.
obstacle will
Sir.
be formed over the screen, but at
Hello,
the
sir.
same time, okay, okay,
ଆପଣ
now
ସ୍କ୍ରିନ୍ ସେୟାର କରିଛନ୍ତି କି?
okay, I'm okay. Again, come to our topic. So, when the obstacle is kept on the path of the light, what will happen? You'll see that light will bend at the corner of the obstacle and enters into the geometrical shadow. The geometrical shadow, you see, this is a source of light and this is a screen here. This is a screen and this is obstacle. So light will obstructed here and it will form the shadow is here. So from this extreme position of the shadow of this obstacle. But you will observe that at the corner of obstacle at this position, a part or a portion of light bends and enters into the geometrical shadow region. This is the geometrical shadow region of this obstacle, and you will see that a part of the light enters into this shadow. So that it deviates, light deviates its rectilinear propagation. Rectilinear propagation, light moves along a straight line. We know it, but you see that light, or you will observe that light will bend at the corner of obstacle and enters into the geometrical shadow. And that phenomena is called diffraction. So this is the important property of light. by virtue of which light, the phenomena of bending of light while passing near the corner of a obstacle whose dimension equivalent to the length wavelength of light used, then we call diffraction. Diffraction is the phenomena of bending of light at the corner of while passing near a obstacle, or the bending of light at the corner of a obstacle while it is passing near the obstacle is called diffraction. Diffraction is the phenomena of bending of light at the corner of obstacle when passes near it is called diffraction of light. So you get the diffraction patterns over within the geometrical shadow of this region. So therefore, in order to get the diffraction pattern or diffraction phenomena, we need there are three essential things for required for getting the diffraction patterns. What are the things? First, source of light. Second, obstacle. Third, this is the screen on which the things can be obtained. So this is the essential apparatus for needed for getting diffraction pattern, that is source of light, obstacle, and screen or human eye. By we now the type of the diffraction, how many types of diffraction? Actually, on the basis of the position of screen and position of source with respect to the obstacle, the position of screen and position of source with respect to the obstacle, the diffraction can be classified in two categories. One is Fresnel type of diffraction, other is Fraunhofer types of diffraction. Fresnel is the name of the scientist who studied this type of diffraction, and Fraunhofer is also name of a scientist who studied this type of diffraction. So the Fresnel type of diffraction, if the source of light and the screen both are at finite distance from the obstacle, it is finite distance and it is also finite distance. When the source of light and the screen both are at the finite distance of the obstacle, then the type of diffraction often is called Fresnel type of diffraction. Okay. So Fresnel type of diffraction, the diffraction which is produced on a screen which is kept at a finite distance from the obstacle, and the source also at the finite distance from the obstacle. Then this is called Fresnel type of diffraction. Another, Fraunhofer types of diffraction. This type of diffraction, either source or screen or both, either source or screen or both are at infinite distance from the screen. Either anyone, maybe source, maybe screen, or maybe both. Whenever both, either source or screen or both are infinite distance from the obstacle, then the type of diffraction obtained is called Fraunhofer types of diffraction. Okay, this is your what is diffraction and what are the type of diffraction, you know. This diffraction is the important property of electromagnetic wave, that is the deviation from the rectilinear propagation of light while passing near a obstacle whose dimension is equivalent to the wavelength of light is called diffraction. And you get, basing on the position of screen and source from the obstacle, it is of two types. One is your Fresnel type of diffraction, other is Fraunhofer type of diffraction. The diffraction which is whenever the source and the screen are at finite distance from the obstacle, the diffraction type is called Fresnel type. When either source or screen or both are at infinite distance from the screen, then the type of diffraction is called Fraunhofer types of diffraction. So the systematic explanation of the Fraunhofer diffraction the systematic expansion of diffraction was first given by Fresnel, the scientist Fresnel, on the basis of Huygens-Fresnel principle. Huygens studied the Huygens explained what is wavefront regarding the propagation of light. Huygens stated the principle. According to him, you know what is the primary wavefront, and that primary wavefront is considered while explaining the phenomena of diffraction by Fresnel. So that Fresnel explained the phenomena on the basis of Huygens and Fresnel principle. According to the Fresnel, diffraction is attributed due to mutual interference of secondary wavelets from the different part of same wavelength by considering phase difference. That means, the primary wavefront is obtained. You see here, this is a source of light, and you see this is a primary wavefront. This is your primary wavefront, and each point of the primary wavefront is called wavelet, and these behave like a source of light, like original source. So you see, this is original source, and this is your primary wavefront, and each point of the primary wavefront is called wavelet, which behave like a new sources of light, like original source. So in the primary wavefront, you get a large number of wavefronts, sources, or that is wavelets. According to Fresnel, the light from each wavelets interfere. This is wavefront. Light from each wavelet, this is wavelet, interfere with each other with different phase difference and produces the diffraction patterns over the screen. So diffraction pattern, how diffraction pattern is observed? In practically, now let us see how the diffraction pattern is observed. You see, suppose this is a point source of light, and this is a spherically obstacle or spherical opaque object. So when light from this source passes near it, you see this is the geometrical shadow. Geometrical shadow means shadow of this sphere. If it is a spherical, you get the spherical shadow. If it is rectangular, you get the rectangular shadow. That is called geometrical shape of the shadow. So you see here, this is a source of light, and this is spherical obstacle. So you get the spherical shadow. At the same time, you can observe that at the central point of the shadow, there is bright point, or there is no light. So this no light means this is due to the diffraction of rays. So experimentally, it is observed that whenever spherical obstruction is kept on the path of the monochromatic rays, there will be a bright spot at the central point of the geometrical shadow, and that is nothing but the diffraction pattern. Okay, you see here, this is a opaque ball, opaque or obstacle. Then this should be a spherical shadow, but at the same time, will you observe that there is a bright point at the central point of this shadow, and that bright point is nothing but the diffraction patterns. So you see that bright point is obtained due to the deviation of the light or bending of light at the corner of the obstacle, and this for which you get the diffraction pattern. So this is the experimental observation how diffraction pattern is obtained, and what is the diffraction pattern, how it is obtained. It is explained by Fresnel basing on the Huygens principle, Huygens-Fresnel principle. That means each point of the primary wavefront or wavelet send the light which interfere each other and produce the interference pattern at the central point. Okay, this is the diffraction pattern observed. Now let's come to this diffraction rate. Now the evolution from Fresnel to Fauner diffraction. I have already told you in the Fresnel diffraction, source and screen, both source and screen are at finite distance. But in Fauner diffraction, this either source or screen or both are at infinite distance. Infinite distance from the obstacle. So evolution from Fresnel to Fraunhofer, if you keep here a source of light, then it is the obstacle is here. This is the slit. Slit means this is obstacle. Slit means there is a hole or opening for allowing light, but this is the opaque or obstacle. These two sides are obstacle. So light is passing near the obstacle. So this slit can be treated as the obstacle. So you see here, this is a source of light at the finite distance from the obstacle. When the source is at finite distance from the obstacle, you can make it infinite. If you keep a biconvex lens, and if source is kept at the focus of the biconvex lens, what will happen? If the source, point source is kept at the focus of the biconvex lens, then you will see that what will happen? The light becomes rendered parallel after passing through the lens. So parallel rays always come from infinite. So by introducing a lens in between the obstacle and point source, the source can be treated as infinite distance. So this is the how can you get the or evolution from Fresnel to Fresnel diffraction here. So here keeping the spherical wave originating from the source can be converted into a plane. So here if it is a point source, this is a spherical wave. But by placing the biconvex lens, it becomes a plane wavefront. Plane wavefront is always come from a sources at infinity. Therefore, it is how you evolve the Fresnel to Fresnel diffraction. Now the construction, this is all about this. Now the construction of Fresnel obstruction. I have already told you a slit can be treated as the obstruction. But here in a Fresnel studied this. He studied and he discuss about the half period element. What is that half period element? Fresnel, suppose this is a plane wavefront. This is a plane wavefront. W prime is a plane wavefront and it is a obstacle. The plane wavefront incident on the obstacle. So at this corner, you see the obstructed a plane wavefront W is obstructed by an obstacle, and when it is obstructed by obstacle, according to the property of electromagnetic wave, it bends or it gets diffracted and produces the diffraction patterns over the screen. This is a screen on which you get the diffraction pattern. So you see here, when light is obstructed here, it gets diffracted and produces diffraction pattern here. If this is the extreme position, P naught is the extreme position of the geometrical shadow of this obstacle, then what will happen? What is the produce a diffraction pattern at P naught of the screen at distance? Suppose the screen is at a distance B from this slit. Now, the resultant effect at P due to the rays from each point of the wavefront, that is wavelet, and the difficulty is that you see here. This is primary wavefront. I have already told you each point of the primary wavefront, that is called wavelet, which behave like this source. So according to Fresnel, the each point of the primary wavefront, that is wavelet, light is diffracted and interfere with each point light interfere with each other. Therefore, produces the interference pattern. But here, what will happen? The problem arises. What is that problem? The light from each point of the each wavelet had different phase difference. So the resultant effect at P due to the rays from each point of the is difficult. What is that difficult? There is infinite number of wavelet on each, infinite number of wavelet on the plane wavefront, and that infinite number of wavelet produce a different part difference, and the different part difference result different phases. So in order to resolve or in order to overcome this difficulty, do you follow me? Again, I am telling, from each point of primary wavefront, that is wavelet, each point of primary wavefront is called wavelet. From each point of primary wavefront or wavelet, light gets diffracted and interfere with each other. The problem, what is the problem? There are infinite number of wavelets on a same wavefront. So from each wavelet, the path difference is different. You know the relationship between path different, phase different. When the path difference are different, then the phase are different. So this is a difficult matter. Therefore, in order to resolve this difficulty, overcome these difficulties, Fresnel gave the idea of half period element. What is that half period element? Idea of half period element. What is that half period element? He just considered on the plane wave front, he considered the annular space in order to overcome the difficulty. Half period element. What is that? Give the idea of in order to resolve the different phases from different phases of rays from different wavelength. Fresnel gave the idea of half period element. What is that element? You see, he drawn the annular, the concentric spherical. He draws the concentric spherical spheres of increasing radius, or radius is directly proportional to the natural numbers with the annular space in between them. According to the annular spaces, these are the annular spaces enclosed by concentric circles on a plane wavefront, such that each point of the annular circle is equidistant if you take this annular circle. And this is a point of observation P naught. So each point are equidistant from P. Therefore, all the rays from this annular space have the same path difference, so in same phase. Therefore, the concentric circles on the plane wavefront such that each point of the annular circle is equidistant, same distance from the particular point P naught of the screen. So in order to order P, the distance of this, the center, if the central point is B and he draws the radius, the distance must be B plus lambda by 2. This is B plus 2 lambda by 2. This is B plus 3 lambda by 2. This is B plus 4 lambda by 2. Therefore, he draws the circle in such a way that the distance of each circle varies, or difference of distance is lambda by 2. Lambda by 2 distance means the phase difference equal to pi by 2. Therefore, the rays of light from one annular space is the phase, and the other annular, the phase difference between the rays in between two consecutive annular space is pi by 2, because the path difference is, if this is the path B lambda by 2, this is B plus 2 lambda by 2. Therefore, path difference between the rays from two consecutive annular space is lambda by 2. Therefore, the phase difference between the rays is equal to how much? That is pi by 2. So this is called half period zones, half period elements. Okay, what is half period element? The annular space in between the concentric circles drawn over the plane wave, imagined over the plane wavefront, having path difference lambda by 2 is considered as half period zones. Okay, this is half period zone, about half period zone. So now it is not, time is not sufficient to calculate all these things. So just I am writing the area of each half period zone. Half period zones means the annular space in between two concentric circles. The area of the each half, this is the annular space. You see, this is the annular space, and the area of annular space is equal to pi b lambda. Pi b lambda. Each annular space are same. So, sir, when it is wider, then the annular space is smaller or shorter. So, area of each half period zone is equal to pi b lambda, and the resultant amplitude due to n zones at any axial point is equal to any axial. This is the axial point. P naught is the axial point. Therefore, the resultant amplitude, or due to a number of zone or any axial point, is equal to how much? That is an is equal to, this is due to nth zone, constant times an bn by bn 1 plus cos theta. Theta is the diffracting angle. Diffracting angle, the angle bends, that is diffracting angle theta. So now the phase difference between two consecutive zones is pi by 2. This is all about half period zones. Okay, now half period zones is over. Next, in your course, follow your course of study, you will see that I have discussed the Fresnel diffraction, half period element. Next, come to zone plate. Zone plate, you see zone plate. Come to zone plate. Zone plate, basing on the idea of or applying the concept of the half period element, a plate is made. A plate is made on which a special type of plate, a special type of optical device designated to block the light from alternating half period zones. It is made drawing. Just a concentric circles are drawn over a plate with the radius proportional to root over natural numbers. Rubber are drawn over a plane plate on a plane plate, and with the alternative annular space are blackened or are made opaque by blackening it. So a special type of optical device designated to block light from alternating half period zones. It is made by drawing concentric circles over a white plate with their radius proportional to square root of natural number and shading the alternating zones. Alternating zones are shaded. On a white paper, concentric circles are drawn whose radii are directly proportional to natural numbers, and each alternating zones are blackened or shaded so that they become opaque, and the remaining alternate zones are transparent to the light. And this is the zone plate, and it is based on the principle of half period elements. It is made of the half period element. So, what is zone plate? Zone plate is a special type of optical device designated to block the light from alternate half period zones. These are the zones, all the annular spaces are zones, and this is zone plate. And this zone plate behave like a biconvex lens. So from each alternating zone, light transparent, and from alternating zones, blockage zones, the light is diffracted from at each edge of the blocking zone. Okay, this is block zone plate, and it is behave like a biconvex lens. And you will study from your book how it will behave like. What is zone plate? What is the basic principle of the zone plate? You know it. Now let's come to, we'll go for zone plate is over. Diffraction patterns of a straight edge and slit wave using half period zone analysis. Now diffraction pattern by straight edge. Straight edge, straight edge. So you see, this is the straight edge, and this is the obstacle source of light, and you see this spherical wave front, and it is obstructed here, and the direct light is coming there, and the obstructed light is there. So the geometrical shadow of this is equal to from this P0 to P0 onwards. So this is the geometrical, the edge position of the geometrical shadow is P0. But what is about the positions of the skin inside the P0 or inside the shadow region? This is the shadow region. As we go, you will observe that practically, if you will perform the experiment, you will observe that as we go from P0, this is P0, which is inside the shadow, point P define the edge of shadow. So intensity, if you move from P0 to P0 to P prime, the geometrical intensity is gradually decreases. Or in other words, if we go from P prime to P0, the geometrical within the geometrical shadow, the intensity increases gradually. It is your practical observation. So this is the edge point of the shadow, and this is far deep from the geometrical shadow. A point far deep or inside, deep inside of the geometrical shadow. You will observe if you move from P prime to P naught, you will observe that the intensity of light increases gradually toward P, and gradually increases. And at P naught, the inside it is totally zero. It increases, and P naught becomes bright point. This is the bright point. And at P naught, the intensity, if I the initial I naught is the intensity of the rays at any position P, but you will observe at P naught, the intensity is 1/4 of the intensity, original intensity I naught at P. And P naught, from P naught to move downwards or move to far inside the geometrical shadow, the intensity decreases, and at P prime, the intensity becomes zero. But at P naught, at the extreme position, S position, the intensity is 1/4 of the original intensity of light. Next, you see the P point is called central maximum position, and you see this is the maximum intense position, and gradually increases. The intensity, you see the peak value decreases gradually. And the diffraction fringes are not equal spacing. The diffraction fringes, so this you see, this is the intensity, so the width not equal spacing, not equal spacing. Diffraction from the single slit, this is all about your diffraction by straight edge. Now, this is straight edge. Straight means thus it is a edge. It is obstacle standing here. So this is. But if you take the slit means it is just two straight edge. In order to observe the diffraction due to single slit, Fraunhofer observe Fraunhofer diffraction. Either screen or source should be. You know, I have already told you in the Fraunhofer diffraction, the either source or screen is at infinite distance, or both are infinite distance. So in order to observe the Fraunhofer diffraction due to single slit in the laboratory, so infinite distance is required. Actually, infinite distance is not required at all. If you place a point source at the focus of the biconvex lens, then the ray becomes parallel, so that parallel plane wavefront are formed. You know, the plane wavefront is always from the infinity. Therefore, you can get the plane wavefront from a point source by placing a biconvex lens. So when point source is kept at the point focus of biconvex lens, will get the plane wavefront, and therefore this is treated as a wave source at infinity. Now the plane wavefront incident on the slit, this is the slit. Slit means this is the opening, small opening of width B, small b, through which light can pass through. But these are the outside this they are opaque. Therefore, when light passes at the corner of this corner or edge of the slit, it bends, and here it bends, so diffraction obtained. Therefore, the bending light diverge from each other, and you can make to focus it at a screen at the finite distance by using another lens L2 when N2 lens is used here. So you see here, I'm reading in order to observe a small laboratory impossible by keeping the source focus of the biconvex lens, so the plane wavefront parallel to the incident on the single slit, then parallel diffracted wavelets are made, focus on one another, the nature of diffraction pattern shown in the figure. So here you see that the position P naught, the maximum intense point obtained, and the both sides the intensity decreases gradually. So I am showing another figure here. At the P naught, the intensity maximum. Then the other side, the intensity of central spot is maximum, and located at P naught, which is called principal maxima. And the peak intensity is on the other spots on the either side of the central field decreases rapidly. It decreases rapidly. The width of the central spot is twice of the width of the spot. You see the width of the spot, this is the width of the central point is much more or twice of this. This is the secondary maxima, and the width is like this. This is the width. Here, this is the width. You see the width of the principal maxima is twice that of the width of the secondary maxima. You will see that the here by the diffraction due to single slit, you get a principal maxima, and the which is and the intensity of other peaks are secondary maxima. The width of the principal maxima is twice that of the other secondary maxima. So if you calculate what is the intensity at any position, the width of central point twice that. The intensity you can calculate at any point can be calculated. The intensity at any point I is equal to I naught into sine beta by beta the whole square, where beta is equal to pi b sine theta by lambda. B, you know, b the width of the slit, and lambda is the wavelength of light used, and theta is the diffraction angle. How much angle made by the light while it get diffracted. If the light initial duration this and light bent at this, that is the theta. Therefore, the intensity at any position I is equal to I naught. I naught means maximum intensity before diffraction, sine beta by beta whole square. So this is all about the diffraction by single slit, and you know what is the nature of diffraction patterns on this scale. Due to single slit, the diffraction patterns is such that a principal maxima is obtained, and whose intensity 1/4 of the intensity, original intensity, and as we move from either side of principal maxima, the intensity decreases gradually, and the secondary maxima are obtained. Generally, the width are not equal. The width of principal maxima is twice that of the secondary maxima, and the intensity is calculated like this. Now let's come to diffraction by double slit. Double slit, I have considered single slit here, and it is one slit. This is another slit. A1 one slit, B1 another slit. If the width of the slit is B, small b, and in between is the opaque or the obstacle object is B1, A1, B2, that is same A. Therefore, the distance between two consecutive slits is equal to B plus A. So here you see the experimental arrangement for double slit, and it is a source of light which is kept, point source of light kept at the focus of a biconvex lens, so that the rays become parallel to each other. So a plane wavefront incident on the double slit, two slits. This is the plane wavefront incident, and after it get diffracted, and the diffracted rays are collected by another another biconvex lens, L2 or lens, and they are made to focus at P theta and P naught and P theta. So both the slits have the same width B and opaque space A. Therefore, the distance between two similar points, that is equal to this point and this point are similar. This point similar. This point similar. So distance between these two similar points is B by A. That means similar point one means the rays from the two similar points are in phase with each other. So the diffracting waves originating from any slit, the diffracting wavefront originating from any slit and traveling along axis of the lens are focused at P naught, okay, and which becomes peak of the central point. And the diffracted wavelets originating from either side and moving at an angle theta are focused on P theta. These diffracted are focused on P theta. So both the slits give their diffraction pattern, and nature of diffraction pattern are like this. Nature here see something different due to single slit. The peak is not much more. Here the diffraction pattern consists of a number of equal each. You see the space between two width of the maximas are similar. The intensity are not equal to with the central fringe. Central fringe is slightly more than that, but not equal. And but the width of each maxima are same. Therefore, again the bright and size. So the intensity are not equal with central spring and brightest spring, central spring, the bright spring, and decrease gradually either side of zero and become zero. But the distance is same. The intensity at any spring, I theta means at the position, this is P naught, any spring, any arbitrary. So that for I naught sine beta square by beta whole square cos square gamma, where cos square gamma is introduced here due to double slit, beta is same as pi b sine theta lambda, but gamma introduced here, gamma is equal to pi by lambda d sine theta. What is d? D is the b plus a, that is distinguished the distance between two corresponding point of two slits, that is b plus a. Therefore, it can be calculated and or it has already been calculated in your books. You will follow the books and you can find the intensity at any position I theta. Theta is the angle diffraction, that is 4 I naught sine beta by beta square cos square gamma, where beta is equal to this much and gamma is equal to this much. Okay, this is all about your single slit. Now let's come to diffraction by multiple slit. Multiple slit, it is not visible clearly. Multiple slit means when the number of slit is not 1, 2, it is more than 2. When the number of slit is more than 2, that is called a multiple slit. So here the rays, a parallel rays or the plane wavefront that can be made the light from infinity, that can be treated as the light from infinity. A point source is taken at the focus of a biconvex lens, then it be rendered parallel. So a plane wavefront, that is plane wavefront incident a number of slits, a multiple slits here. Now you see here what will happen. Discuss the diffraction pattern produced by a number. Suppose you have considered capital N number of vertical slits of width beta. So distance between two slits, suppose A, so that the grating element, or you can say the distance between two corresponding points is A plus B, and diffraction pattern which consists of vertical springs. So if you calculate this, the plane wavefront incident on the arrangement of n slits and the diffracted rays interfere with another and resulting the springs. So the rays diffracted from each slit. There is n number of slits. So the plane wavefront is incident on the arrangement of n slits, and the diffracted rays interfere with each other, resulting the spring. So from n number of slits, diffracted rays are obtained, and the diffracted corresponding point means the point distance between two corresponding points from B plus A, and the rays from corresponding point have same phase. Therefore, these diffracted rays interfere with each other, and we get the interference pattern. If you calculate what is the intensity due to number of springs, that is equal to multiple springs or n number of springs at any position theta, I theta is equal to A square sine beta square by beta square sine square n gamma by sine square gamma. So here n is the number of slits. It is observed that the principal maxima is n slit pattern corresponds to the position of this double slit, or you see here number of central springs here. Number of central springs, and all the secondary peaks are same value, same width, but the width of the central peak increases. Here the width is pi, while here the width is 2 pi. This pi by 2 pi, it is here is a 4 pi. So 2 pi, okay. This is pi, 2 pi, 4. So increases. So this is all about your diffraction due to n number of slits. Let's come to diffraction due to grating. Diffraction grating. That is, diffraction grating means an arrangement of large number of equidistant narrow vertical slits. I have the basic difference between n number of slits and grating. When a number of slits also taken as grating, but grating means when a number of slits infinite number, large number of slits which cannot be counted. So the arrangement of a large number of equidistant narrow vertical slits is known as diffraction grating. Okay, so practically grating plates are made of the first grating were made by Fraunhofer with nearly 200 wires on centimeters on a frame. A grating were made by ruling fine lines with a diamond pen on the glass plate. A glass plate, you may take a glass plate, on the glass plate draw number of line by diamond pen. Diamond pen can cut the glass, or glass can be made opaque by drawing lines with a diamond pen. You know, the glass are cut by diamond pens. So that by the using the diamond pen, we can draw a number of lines so that the transparent part between the lines acted as the slit, and while the broken lines are drawn over a glass plate by using diamond pen. So when a broken lines are drawn over the diamond plane, you will see the transparent part between the two lines acted as a slit, while the ruling shelf act on the. You just draw the parallel lines, number of lines by diamond pen. So in between two lines, this is transparent. So this is behave like slit, and the line is opaque, becomes opaque. So a diffraction grating plate can be made. When the diffraction occurs, we have seen that the monochromatic range of light of wavelength lambda, the principal maxima is given by grating equation. Principal maxima, it is grating equation. This is equation d sine theta 1 by n lambda 1, n012. With the experimental arrangement, we get a principal maxima as is the line. If another light used, this is like this. So when while the light is used, the central image will be white. If you take the central image, a bright light, if you write the monochromatic, in place of monochromatic light, you take the bright light, then the central maxima will be white, while the other will show the color of continuous film. So what are the observation? It is observed that the spectrum exists both sides of the diode beam. Apart from the first order, second order, third order spectrum, they are also present. So different spectrum lines are not equally bright, sharp. They depend on the energy levels and transmission atom given. Just you see, this is the central maxima. This is white, but this is the color spectrum. White color spectrum. So sharpness decreases as we move away. Order with the order. You see, this is the order. Thus, it is the application grating plate. It is the experimental plate. We have discussed about the diffraction due to multiple slits, n number of slits, and when this is practically a plate is made of glass plate over a glass plate, drawing the parallel lines by a diamond pen, then the glass is transparent. In between the gap between two lines become transparent and so behave like slit, and others opaque. And from this, using this plate, we can get the grating, the diffraction over the screen. If you use a monochromatic light, then the strips are obtained over the screen. If we use the white light, what will happen? The white light, for white light, we get, this is the white light, you get the central bright ring, and on the sides of the both sides of the bright ring, you will get the color spectrum. The color spectrum, what is your observation? I have told you the observation is like this. The observation is that apart from first order, second order, or third order spectrum, they are also present. Grating, different spectrum lines are not equally bright, equally sharp, and this depend on the energy levels and transition of atom. So this is all about your, if the grating element has n 100 number of 200 number of lines, then there will be two number of if the number of slits, then suppose the number of slits is n, then becomes the angular width of the principal maxima this much. This is all about your second block, the fourth, that is your third block. This is your third block of the course. Next on tomorrow, I think tomorrow, so thank you very much. Next tomorrow, I'll take your last class and I'll discuss block 4, ledger and optical fiber. Okay, thank you very much. Let us stop your class. Or any question? Any question? Anyone? Any question?
No, sir.
No, sir.
Okay, thank you very much. Let us stop here.
Have you all written your element number? Have you
Yes,
all
sir.
written your element number?
Yes, sir.
Write your enrollment number so that your attendance will be recorded. Yeah.